So I will skip the multi-cycle version, come back into it, because I want to talk about the branches, right? So control dependency and branch prediction. The single type of hazard, so we discussed data hazard due to data dependency between instructions, structure hazard, again, two function units try to access the same hardware. The third type of hazard is called control hazard. It's another type of dependency, but it's control dependency, not data dependency. Because if you have branches, especially conditional branches, you need to figure out what instruction to fetch next, right? And in that case, there is a dependency between this branch and all the subsequent ones. Right? Good. So just to understand the problem of branches, let's try to think about kind of couple of questions. When do we read the instruction from the memory? First of all, when do I know what instruction I want to execute next? This is at the fetch stage, right? So I bring in the fetch stage the subsequent instruction, while the early one is in fact going through the decode, right? That's really pipeline, right? So once you move from the fetch to the decode for an instruction, you increment program counter by 4, go ahead and bring the subsequent instruction. This is if you don't have any branches or any control flow, if you just move sequentially completely, this is what's going to happen. Every single instruction is next to the previous one in the memory. You increase program counter by 4, go ahead and bring it. Good. Now, a second important question is, when do we know branch outcome? What does it mean by branch outcome? When we discuss the branch types, especially the conditional ones, the terminology of a branch was something like this. BEQ, assume for example it's branch equal, and then I'm comparing two registers, R1 and R2, and then I want to jump to some label, some address, right? So what really happens in, what is the operation of, what is the operation of a branch? Simply, I want to compare R1 and R2. At which stage I'm doing that? Execution stage, using the subtractor. Remember, we went through in detail of how to do that thing, right? In our ISA lecture. We said, I go to the ALU, subtract these two, take the 0 flag, and simply based on this, whether the 0 flag is true, in that case, I will have to update the program counter by the math related to this offset, correct? If they are not equal, then what do? I take the normal path, which is program counter plus 4. Which means I do figure out, this is called branch resolving. So I do resolve the branch in the execution stage, right? So put the answers of these two questions together, and you will understand why branches are problematic. Branches dictate what instruction you execute next, you fetch next, but then you only know that at the end of the execution stage. While you need to fetch the instruction at the fetch stage. If you look into your normal pipeline, you would have a fetch, decode, execute, memory, write back for the branch. And while you decode the branch, you fetch the next one. You only know what instruction to fetch here, but you want to fetch it here, right? This is why if you do nothing at all, you would have to wait until you figure out which instruction to fetch, and then you start fetching it here, correct? Because this is the only time, or it's only by that time you know what is the correct instruction to fetch. So the branches, without any novel solution, imposes 2 cycle delays in this pipeline on you to fetch the subsequent instruction. Make sense? Good. Why that's the case? Because again, a branch is trying to tell me what instruction to fetch next, and I only know this at the end of the execution stage, while normally without a branch, I would have fetched it here. So I was delayed by 2 seconds. Good. So what to do when a branch is actually taken? So it's called branch recovery. So one solution, if you don't have any, again, forget about branch prediction for now. If you don't have branch prediction, what I can say is, okay, you just move in normally, because by that time, you don't even know it's a branch, right? And this is the third question. When do I even know if it's a branch? I was telling you that, well, if this is a branch, you don't fetch here, you have to wait until the end of the execution and then fetch. But you should ask the question is that even when I try to fetch that one, I don't know that this is a branch. The hardware doesn't know that it's a branch. When do I know it's a branch? when I decode it, right? I only know the instruction when I have the opcode, right? Makes sense? So I only know when I decode it. By the time I have already fetched one, correct? So which means you have already fetched the subsequent instruction. So you do a fetch, decode, and then when you try to execute, you figure out, for example, no, the branch is in fact forcing you to jump. Then you have to flush, right? And this is what we call a branch recovery. If you don't do anything to fetch, well, another question. This instruction that I'm fetching here is which instruction? Now the branch has two possibilities, correct? I either execute the next one, or I jump to the label and execute the one at the jump, right? It's like an if else. You either execute the if or the else, right? Now, by doing this, which one I'm fetching right now? Yeah. The one directly after, subsequent one, right? I don't even know it's a branch, so I just do what I do normally, program counter plus 4, right? So bring in the subsequent one. But by that time, you are either true or false, right? You are either, well, I don't need to jump, in this case you are fine, or I need to jump and then I have to flush my pipeline. Make sense? So in a sense, if you don't do anything, this is as if you predicted the branch when, well, we call this not taken. You will never jump, right? So it's a static predictor in a sense. If you don't do anything, as if you're assuming that I'm always going to, the condition will always evaluate to false, right? Will this happen? Well, maybe not, right? And in this case, you have to do something. This thing is called branch recovery, which means the extra cost you need to flush the pipeline to bring in the subsequent instruction. So normally, without any prediction or anything, I bring in the next instruction, decode it. By the end of the execution, I would have already known. If the condition is false, you continue and you don't pay any cost. If the condition is true, you have to flush and bring in the subsequent instruction. So you paid an extra 2 cycles plus some extra delays for the flushing. That's a very good question, because we need to differentiate between two things, and this is what Lab 2 is also doing. In a branch, I need to figure out the answer for 2 questions. The first one is whether it's even a branch or not, and this is what you know at the decode stage, right? But the second thing is, if it was a branch and if there is a conditional branch, the result of the condition, like simply the comparison of this R1 and R2, this only happens at the execution because you use the ALU to subtract, right? So the 2 questions are whether this is a branch or not, and the second one is if it was a branch, a conditional branch, whether the condition evaluates to true or false, right? And these 2 happens at 2 different times, right? And hopefully, if you didn't reach that point in Lab 2 yet, this is what's also happening in Max, right? You are asked a question, when do you know whether it's a branch, and when do you resolve the condition? And the documentation in Maxim also goes through this in the pipeline. Good? Okay, great. So we call this, as we said, a branch recovery. Simply, what do I do if I really need to jump? And in this case, you just simply flush and then bring in the second one. The good thing here is that it's a little bit low cost, because if you think about this instruction here, only 2 cycles elapsed. In computer architecture and pipelining, there is a very important concept of a permanent state. What does it mean? And we will also revisit this later on for out of order. If this instruction, for some reason, was able to write to the register file or the memory, like do the actual write back, would I be able to basically flush and just bring the subsequent instruction? No, because you wrote to the register file. You changed the state of the system permanently, right? You see what I mean? If you wrote to the memory, then you wrote to the memory. I mean, how do they recover? There's no way to recover, right? Because you lost the whole data. Well, thankfully here, in that situation, only 2 cycles elapsed, and because this is in order pipeline, by the end of the decode stage of the subsequent instruction, I didn't do anything really, right? I only put in the instruction. I understood its add, for example, but I didn't really do the execution, didn't write to the register file, did nothing. So it's just safe to say ignore it and bring in the subsequent one. Make sense? So it's a safe recovery, basically. It still costs 2 cycles, but you didn't lose the permanent state of the system. Make sense? And by the way, this is one very important point for people that are interested in security, because most of the time, what they try to do is to try to do a sequence of instructions that do unintended, well, it's a hack, basically, right? It's unintended by design, but change in a state of the system. If you're able to change the state of the system, which is basically a vulnerability in the system, then you have modified the control flow. And in that case, you are able to do something that the system is not intended to do, right? So most architectures try to guard against an unintended change in the system state, right? Because it can lead to huge consequences. Okay. So assume I don't want to suffer. Assume I don't want to suffer these extra 2 cycles, right? These 2 here. Assume I don't want to wait. What can I do? I have 2 questions. Last lecture we said, okay, if you don't want to wait, a very normal behavior in computer architecture that people kind of accuse them that they use it too much. Speculation. You don't know, well, try to speculate. If your speculation is correct, you save 2 cycles. If it's incorrect, you lose some, but whether you lose the same thing or not. And we just said, by in fact doing nothing at all, you're just doing a static speculation, right? You're just assuming all the time the branch is not taken, you're not jumping, and you're executing the subsequent one. So if your branch type, for example, means I'm always going to jump, like a for loop, for example, that has very large, it goes through a very large array, which means most of the time it's in fact taken because you have to go through the loop again and again and again and again, right? It's only the last element where it's not taken. So if you just assume it's taken all the time, you are wrong 99% of the time. In fact, if you reverted your speculation to be not taken, you might do better, right? So there are static kind of predictions. This is one of them by just assuming, well, I'm taking all the time, but it might not be the right way of doing it. Good. And we built what we call speculative execution. Speculative means you execute assuming something, and later on you try to figure out whether you are correct or not, right? The good thing about trying to, maybe we don't have time to go through it in detail, let's see, but in reality, if we didn't manage to finish, I might take the first 10 minutes of the tutorial because it's important also to explain the stuff there. So what we stopped at right now is there is a static branch prediction. Static means I always assume I jump or I always assume I don't jump. Well, the advantage of a static prediction is very simple to implement in hardware. So we had a multiplexer, if you recall from the ISA, we had a multiplexer that picks between the normal path and the path. In fact, it was picking from 3 things when we built it at the end. It was picking from program counter plus 4, normal instruction, or it's picking from the offset plus sign extension plus adding to the program counter if it was a traditional branch. What was the third one? If it was an absolute jump, right? I just take the 24-bit of the immediate value directly to the program counter, correct? So we had 3 options here, but here I believe it's ignoring the absolute jump and only looking into the branch plus the normal path, right? And there was a selection line that picks among it. This selection line, in fact, should also be fed by the 0 flag, correct? So if I want always to make it take it, what do? Well, always pick that path, right? Always pick the path that goes out of the branch, right? But there is a problem here, is that this path is going to wait, this one here, has to wait for the ALU to execute, right? But I don't want to wait for the ALU. As your friend here was saying, well, you wait for the ALU to determine the condition, but you already have the offset from the request state, right? So I can take the offset from here, through the register file, do some sign extension, take it from here, and feed it directly, right? So this is the change I want to make. Instead of waiting for the 0 flag to tell me that you can't take that path, I force the selection line to always take that path if this was a branch instruction. I was talking about there is a mux here that should in fact select between these 2. Okay, so let's go to the actual detail. These slides, I don't think they have the detailed implementation, but I simply do the following. Normal path, program counter, and then program counter plus 4, right? So this is the plus 4 path. I add here, I feed, so I just go the normal path, right? Or I do program counter plus 4 plus the offset, correct? But this only happens if it was a branch instruction and the condition was true, correct? Normal. This is what we designed in the ISA lecture. But then, when do I take that one? Yeah, it's here. That's basically the mux. right? We took that mux from here, put it here, right? So there is a mux selection line here that picks among these two, right? So if this is your selection line of the mux, you have the path of the program counter plus 4, which is the normal one, or you have the path that is coming from the branch. If you look into that selection line here, where it comes from, it comes from this AND gate that simply takes the 0 flag, which is the result of the condition. And there is one additional thing here. What is this thing? What does this wire really mean? There is one missing piece, right? Remember, I need to take that branch here, this wire here, with two situations. If the result of value is 0, but that's not always true, because I might be doing a subtract operation and the result is 0. So when do I pick that path? It has to be a branch instruction as well, right? So there is an AND gate that simply takes the 0 flag and takes the opcode of the branch. And in that case, you select the path of the branch. Now, if I want to predict always taken, what do? You have to select that line to always go to that path, right? Correct? So, for example, if this was 0 and this is 1, you always pick it to be 0. Makes sense? But you always pick it always 0 if it was a branch, because otherwise you keep jumping all the time and you don't even have an immediate value, right? For a normal operation. So you get rid of that 0 flag, but you still keep the opcode of the branch, right? So this is as if this is always 1. Because always taken means always the condition is true if it was a BQ, and which means you assume that this is always 1. Make sense? Good. What we have been doing with always not taken is in fact do the other way around. I'm always taking that back. Right? I'm always assuming it's program counter plus 4. Forget about this one. Because in fact, before I fetch and decode the branch, I didn't even know it's a branch. So this was evaluating always to false. Then I'm taking that one. Right? The main purpose, and we stop here, the main purpose of a branch prediction is simply to answer this thing, whether it's a branch and whether the condition is true or false. So the whole point about a branch prediction is in fact to predict the inputs of this AND gate. Make sense? So let's stop at that point and continue from it at 12:30. Thank you.
Here's the differential, and here the execution path, and here is the decoding. By that time, the